Trying to be it, pure experimentalists trying to do their best. Okay, so let's continue these things. Essentially, what we're doing here is give you a, sorry. Now, let me first of all start, like the others, saying a few words about Abdus Salam. Of course, many things can be said already, so I have to be relatively brief, but I'd like also to witness this occasion by making a couple of transparencies. Here is, let me remind you that it was born exactly 90 years ago on the 29th of January. Let me also point out that being proud to see today one of the last steps in Electro-Weak unification standard model, which you already heard a minute ago, with experimental observation of the Higgs scalar, a subject that he had initially contributed so greatly. Let me also point out that Abdus Salam would have been equally proud of the progressive emergence of developing countries, the new remarkable and worldwide developer of science and technology, to which he had so intensively anticipated from the early times when these concepts were still vastly unknown to most of us. So that's essentially. And the question is, of course, behind Salam there is a dream. The dream is from here to infinity, and the Planck mass is somehow the goal, all this thing which he's talking about. Salam major and most notable other achievements include also many other domains like the Patti-Salam model, like the magnetic photon, vector meson, grand unified theory, supersymmetry of SUSY. As much as many others, he was deeply convinced that some new physics had to be found at energy much higher than those that any accelerator would ever be capable to provide, in which nature has evolved since from the initial Big Bang, presumably from the famous 10 to the 19 GeV to the now explored LHC energies domain, or only 10 to the 3 GeV. Several of these initiatives have so far failed to correspond, of course, to experimental discoveries, and there remain the open question, like, let me mention a few. Supersymmetry, the new realm of symmetric particles. Why should supersymmetry to be together with LHC? Most likely may be associated to gravitation, therefore to much higher energies. The decay of the protons is another very important question experimentally we have to discover. A famous statement, we said diamonds are not forever. Glasgow was saying that. The true nature of neutrinos, the universality of the CP violation, the existence of monopoles, relic monopoles, all these questions have been ahead to us to be discovered. But it's important to say that because of his premature death, Abdus Salam has unfortunately missed the two most extraordinary discoveries which have fascinated him. And let me mention them. They are the dark mass and the accelerating universe. These are new steps after his. Now, let me then come back and discuss a little bit questions about the scientific applications of what I call the CERN-made colliders. The CERN-made colliders are essentially a number of discoveries which we pursued at CERN with the development and successful operation of a chain unique and innovative colliding beam machines in the same 27 kilometers tunnel with first LEP and later LHC experiment. Here is the drawing of the picture. Everybody remembers that. I think it's worth mentioning it. Here is the SPS, PS, and all the other places for which lots of interesting physics was done before. And here we are concentrated on this famous LEP tunnel of 27 kilometers diameters. And there are three fundamental activities there which I'm mentioning, which I will discuss in a little while. First is LEP 1, which collected as many as 4.5 million Z0 events for each experiment. The second is LEP 2, which is about 10,000 WW pairs per experiment. And the third is LHC, of which many other speakers will tell us more today, in which a new particle has been observed, 125 GeV by Atlas, CMS experiment, both representatives here. Thank you for being here today. And that is an agreement with the Higgs bosons. Now, this is essentially the way in which it looks like CMS and Atlas are opposite lines in the beam, and ALICE and LHBB are in fact on the other position. This is the present configuration of the CERN situation. Now, LEP has already been the first step of these massive participations of the experiment. Here, I show you, for instance, 1,000 of physicists already participate to LEP, and also they continue to participate in a new way in which science is being done. Here, for instance, the picture of Nobel Laureate Chet Steinberger in charge of LHC experiments. Here I have a picture of three Nobel laureates together, same thing, which you see there, in charge of the L3 experiments. and I was there, and so was George Sarpak, which now is unfortunately deceased us some time ago. Now I have another picture to show you here. For instance, Schopper and myself, the CERN directors during the construction lab, and on the first day of the first successful collisions of this story of the physics, which goes through lab first and then now gets to LHC. Now, what was the main key behind the discoveries done with lab? It was essentially, in my view, was anticipation discoveries, and which permitted people to know exactly where to look for, both for the top and the Higgs particles. So you can see here the picture of the mass of the top, which was as it was predicted with the accurate measurements from Lab 1 and then Lab 2. And you can see finally the experimental discovery at Fermilab, which coincides with the prediction coming from the small high-order quantum mechanical correction coming from Lab. The second example, that is the Higgs particle. Again here, you can see Lab 2 getting involved into Lip particle and predicting Higgs particle between 114 and about 200 GeV. And then you see then finally, then in 2012, as you will be saying before, the experimental discovery at LHC at a mass 125, 127 GeV is essentially within the predictions of this situation. So the predictive power of lab has been extremely powerful, extremely important in order to prepare people to the direct experimental discoveries. Now, just to those people which are here, let me spend just 1 minute to show you the real picture. A real picture of LHC. And then what is most impressive about this picture is to see the huge dimensions of the LHC. You see how small the curvature is. Now take that curvature. Imagine how much it takes to go around 360 degrees to come back again. And that is the trip you have to do if you want to go and make the LHC be what it is. Now, detectors. Now, they will be discussed later on. You are here. Yen is here to tell us about that. But anyway, here is the detector. And let me show you down here a very important point. That's the imager man. So you can see the dimensions of the size of the experimental program as it's been developed at the time of the LHC. Now here is another picture. Is a picture of quiet main making a big bang. I'm in for that Peter Higgs, which is being photographed here at CMS. I think that's also a very remarkable picture which is worth mentioning. Now, the latest discovery was already mentioned, was done the CMS and Atlas, which have observed this famous data, consistent with the fermionic and bosonic coupling of standard matter. Searches have been performed in several decay modes, however, always in presence of very substantial backgrounds. Experimental energy resolution has been so far much wider than any conceivable intrinsic hit width, which, as you know, is only a few MeV. Results of both experiments also exclude other standard model, Higgs boson up to 600 GeV. And now that's a famous picture, which no doubt you're going to show them and describe again in more detail in your presentation. But I think it's worth mentioning. It's an important step in the history of this laboratory. You can see here Atlas, and you see here CMS, and you see how the peak presents itself in the presence of very substantial backgrounds. Now, let me also, before going any further, touch another point, which is the question of a surprise, which is coming through. There was a presentation in CERN last month. Atlas has just reported the 13 center mass, a 3.6 bump at the 760 GeV in the gamma-gamma spectrum. Roughly coinciding with 2.6 standard deviation XNCMS, a total of 4 sigma. There is the signal. You see there, you see another little peak coming up at about 750 GeV. It's fairly wide, it's 40 GeV wide. And it's some question, which is, of course, is a surprise, which needs, of course, to be further developed. Now, here is the surprise. Now, why, but there are lots of problems which are worth mentioning. Why no bump in the previous ATV data? The gain for a gluon-gluon collision is 5 times at 13 GeV than to 8 GeV, where the 6 times more data were already collected, for instance, by Atlas. And therefore, why did not appear at 8 GeV and did appear at 13 GeV when the ratio should be, if it was, for instance, an example of a gluon collision, scaled up in a factor? Why is not visible in the W boson pairs dominant for the Higgs scalar? So, of course, 10 times most of this is forthcoming. But let me mention here briefly a picture of what we are expecting to have if there was a sort of some extra object of a standard or non-standard type of Higgs object. You see, this is the picture coming from a very old paper by Barger. And you can see here the line of the gamma-gamma indicated there. You see, sorry, where is it? Well, how does you work this thing? There is no way of getting here you are. The gamma-gamma line is there. And now, because this is 500 G, so if you continue further to go to 750 GeV, we see that comparing to anything which is like a Higgs particle compared to the gamma-gamma will be at that level of 760 G, or the order of 10 to the minus 6 of the dominant process would be semi-weak WW, WZ productions, and TT bar and all the rest of the stuff. So, I mean, obviously, if this is confirmed, it's a very strange new object. It cannot be just taking another piece of particle Higgs, but anyway, this will be described, I suppose, tomorrow. Now, let me continue about LHC, and let me therefore mention that what do we expect from LHC? LHC accumulating a certain amount of data. Here is the graph which shows the predictions from estimated errors from ATLAS and CMS. You can see there the various possible objects. You can see here the W, the Z, the beauty, the gluon, gamma, and this is the invisible cross sections. And these are what are presumably what we would expect to have from something like several years of running time in this experiment. You can see there one standard uncertainty. You can see their lines are there. Of course, those are predictions. I mean, maybe different predictions, but they really show that the effect is quite substantial. That in most of the channels, 5% is a 1 sigma level, and obviously there could be, of course, now it's been approved the idea to construct a high luminosity LHC, but of course to go from the present state to that state is very hard. But anyway, it is quite clear that the uncertainties from the LHC are because of the hadronic nature, are very substantial. And let me also remind you the ambiguous discoveries required 5 sigma precision. Now, the question therefore is, what can we do beyond the LHC? I think that the future is the one of getting the best out of LHC, but there is need for a new develop a new program. Tomorrow will be also a discussion on these questions. And now there are too many alternatives which are possible, which have been vastly discussed in the community. One is they produce a ring, a new ring, of about 4 times the LHC, but limited in the square root of S to 250 GeV. So therefore limiting some of the elements, but still it's a possible device. As you see, many countries are thinking about that. Or the other alternative, the linear collider, which is a collision or 2 linear collision of 2 beams, which is has to reach, again, for 1 TeV, something like 50 kilometers circumference. So we are talking about either order 100 kilometer ring or a 50 kilometer linear colliders. And this is a major new technology which needs to be developed. So this project will likely exceed LHC, both in cost and in time schedule. And the other alternative, which is the purpose of the present talk, is mu plus mu minus rings, which are much lower cost and a much shorter time schedule, can be done in a few years, which may easily fit within the existing CERN site or other similar sites, but require the compression of phase space in muon beams with 2 potential alternatives. One is to go directly in the S states, resonance at 126 GeV, in order to observe the 4 MeV wide Higgs without backgrounds. So this is the equivalent to the Z0, to produce just simply the object you're interested in producing, and look at it in all possible decays in the free clean conditions. And the other one is the high energy collider ring, up to about 1 TeV, to look at many other additional aspects of the problem of the scalar particles, and which is a luminosity comparable to the linear collider and so forth. Now, let me say the huge rings, of course, have been very popular. You can see here the many centers which have discussed how to carry out the thing. They go from Japan to China, Russia to CERN, and there is a huge number of alternatives in Fermilab, in CERN, and at West Coast in Texas, and so forth, in Brookhaven. And options, very many of the options are becoming popular around the world, and presumably one of them will have to be built sometime in the future. And now they are called LEP3, TLEP, side fillers, etc., etc. Let me mention, for instance, the situation for as far as Geneva is concerned. You can see here the LHC now looks like a little baby, And you can see, in fact, that this new ring is the one which is should be to build in order to study the next step. You can see here the Geneva Lake. You can see also that the thing is surrounded largely the Jura and Salam. It's quite an impressive story, and it shows you what is really required in order to do that kind of thing within the Geneva area. Now, the LHC and TLAP, you can see the differences in reality. Now, these are very important new steps also from the point, not only from the size, but also from the point of view of the luminosity. First of all, the collisions require a luminosity factor about 500 times larger than LEP 2. LEP 2 was 10 to the 32. This new system has to be 10 to the 34, and it has to use a huge power consumption. This is electric power consumption, and which are similar to the one on LHC. And the other problem is that in order to get that factor 100 more luminosity, 500 times more luminosity, you need extremely vertical emittance with a beam crossing size of the order, let me tell you, 0.1 micron, so 10 nanometers. It has been 3 micron for LEP 2. So it's no question that the development of such a new machine will have a border feasibility. And of course, that will be limited by practical reasons, essentially 250 MeV and GeV, and therefore Higgs, weak Strahlung, double Higgs diagrams cannot be studied by any acceptable P plus V minus ring collider. The other alternative is a so-called linear option, which is now discussable. As discussed in this discussion, we assume to go to 200 GeV to start with, and then 500, eventually 1 TeV. What we are talking about here is two linear devices which are crossing each other, submicron beams colliding only once head-on, and starting from the left and the right, and they are coupling ring there. And there are many models for this. There is ILC, CLIC, LHC, JLC, etc., etc. Now, the total footprint is 31 kilometers for 500 GeV. If you want to go to 1 TeV, then you're going to put another 22 kilometers to be extended to the system to get to the result. Now, let me say briefly the situation. The collisions now are coming with even smaller dimensions. Now, this thing have dimensions, the two beams are crossing each other 50 kilometers apart, one in Geneva, the other in Lausanne. They come together and they hit each other with a precision of 5 nanometers, which is 0.05 microns, each containing 2 to 10 particles, and this repeats 14,000 times a second. Now, there are a huge number of accelerating cavities. The temperature is 2 Kelvin, the same as LHC. The length is 31, I said already. And the other important question, two damping rings which are used in order to prepare for these beams. And they have each a conference of 6.7 kilometers, which is a size, essentially the size of SPS, or if you like, 1/4 of the LHC size. Now, in spite of this kind of enormously large development in ideas, nearly 300 laboratories, universities around the world are now involved in the LHC program. More than 700 people are working on the accelerator design, and another 900 people on the detector development. The accelerator design work is coordinated by the global design effort and the physical detector work by the worldwide study. The estimated cost for this 500 GeV option, halfway option, it's of the order again of 10 billion euro, which is roughly the size of the LHC. Now, the question is, what is the consequences of that? So let's compare the LHC and the various other future alternatives represented here by the ILC 1, 250, then the 500 GeV and 1 TeV situations. And you can see here the various elements as before, and you observe how the improvement is possible, predicted improvement for these systems. Now, the LHC is indicated there, 300 femtobarns. Now, here we have the ring ILC 1, which is 250 GeV, 250 nanobarn. You can see that although the effect is very substantial here when it comes to WZ, in many other aspects, the progress is certainly important, but it doesn't justify the construction of another 10 billion euro device, in my view. This is the LHC with 500 GeV, and this is 1 TeV finally, reaching that point. So essentially, again, an ambiguous discovery requires, as I said, a Wi-Fi sigma. So these machines are probably going to give you, in many of the channels, about maybe a factor 2 or 3. So they're really quite still at the limit when it comes to using the signal, with the only exception being the one of the WNC. Okay, 1% is indicated there. Now, the reason why we need to do this kind of activities comes from the fact that in order to understand the Higgs, is a scalar, is a new particle, we have to accept a number of possible new factors. Here you see, for instance, the situation of this ring, for instance, the 80-kilometer ring in the case of CERN. And you can see here the, sorry, this is not really working very well. You can see here the, sorry, you can see, there it goes. It's already almost dead. Yes, you can see here the where the 8-kilometer ring CERN is coming, so you can only see this point here. But then you can see that many other pieces of information exist, which involve also production of single Higgs, or Higgs to Higgs, and so forth, which require all these cross-sections, which are indicated there, which again, as I say, prove the necessity of doing something all the way to 1 TeV. Therefore, the standard ring is really quite limiting in these particular situations. And those are, in fact, the extra long diagrams and double Higgs boson diagrams, which all have to be, in our view, be brought in order to explain properly the situations in the case of the Higgs production. This requires, obviously, energies of the order of about 1 TeV. Now, the alternative is to cooling with non-Liouvillean accelerators. Now, already in Muon in the 50s, it was realized that some beam phase-space compression may also be necessary from the source of the collision point. I remember Piccioni, O'Neill, and Simon talking about that. And this is coming from the fact that Liouville theorem is putting very strong limits. Any force derivable for a potential, it preserves the six-dimensional phase space. In other words, if you have a big beam to start with, it stays big no matter what you do, provided that you have an Hamiltonian, which you have in most of the accelerator systems. Therefore, there is a need of some dissipative non-Liouvillean drag force working against the particle speed and not derived from Hamiltonian. And there are several alternatives which have been done in the past. Let me mention them here. There is a synchrotron radiation, only electrons, electron cooling and stochastic cooling, which we have done together with Boedker and van der Meer to develop the P-bar-P collider. And now there is a new object coming up now, which is called ionization cooling, which you see right there. DDX losses added to the beam in order to be similar, again, dissipative non-Liouvillean forces. Any of these methods, with accelerated cavity repressing the losses, one can compress the phase space volume, and this is, in fact, the purpose of the proposal, which I'm going to discuss here. And now let me cover the story from antiprotons, for which we did the work, to muons. Phase compressing is essential. In the 80s, we had developed a cell antiprotons in which both stochastic and electrocooling have been used. Let me remind you that PP-bar colliders have permitted the discovery of the Z, the discovery of the W, and the discovery of the top. And run over 30 years, the high energy front, energy limit. Ionization cooling is specific of muons since they have only electromagnetic interaction with matter, and the muon lifetime may be long enough to offer, with the help of ionization cooling, a reasonable number of mu plus mu minus collision in a ring. The concept of muon cooling was first proposed by Boedker and Skrinsky in the 60s and in the early 70s. The concept had no substance until it was developed by Skrinsky and Pomarchuk. About 25 years ago, the ionization cooling was expanded by Neuffer and by Palmer, mostly in the United States. And the development of ionization cooling is very simply described. This is called also DDX cooling, closely resembles the synchrotron compression with a multiple energy loss in a thin low Z absorber, substituting the synchrotron light. The main feature of this method is produces extremely fast cooling compared to other traditional methods. This, of course, is a necessity for the muon case. Transverse metal oscillations are cooled by a target foil, typically of the order of 1 fraction of gram per square centimeter thick. An accelerated cavity is continuously replacing the lost momentum. Unfortunately, the slow muon, the specific DDX loss is increasing with decreasing momentum. It is the opposite of what happens to synchrotron light. The synchrotron light, the fast particle produces more radiation. In order to cool only longitudinal, chromaticity has to be introduced with so-called wedge-shaped foil in order to increase the ionization losses for the fast particles. Now here is shown the two typical situations for the cooling. Transverse emittance is a combination between cooling in one hand and scattering in the other hand. And then you reach an equilibrium value, which is right there, which indicates an equilibrium emittance, in which essentially for hydrogen, for instance, a beta 10 centimeters, you get a relatively small emittance as an equilibrium. And you can see that is, here is the mu momentum of the ring in very small momentum, MeV over C. You can see that invariant emittance is roughly constant. They correspond to a fractions of millimeter radiant for the beam with a hydrogen or absorber. In the longitudinal balance, you have different phenomena here. In longitudinal balance, we have three effects. We have here the effect of the sorry, this is not really working very well. We have three effects here. We have the intrinsic energy loss, and the wedge-shaped absorber, which are really working in reducing the size, and you have the straggling of the beam, which is producing the increase in the error value. And then there is again a balance between the two systems, and the result of that is shown in the next transparency. You can see essentially that it is a longitudinal balance in which the absorber is compensating the various effects. You can see that effect here in a typical example. You see here the effect in the energy spread coming from the fact that the wedge, as I said, is bent. And therefore, particles which come in with a different value at the AOE have a different amount of absorber, which is balancing up the signal to give it equal signal. Now, all that goes into a very well-known story, which goes under the Robinson law, in which it connects the transverse and longitudinal momenta with a value which has to be 2. And this is true for synchrotron radiation, it's also true for our case. And the other question is, we are choosing a specific energy loss, which is about 200 MeV over C momentum right here, because that is a place in which essentially different momentum muons indeed are converging into a constant value, and therefore the effect of the energy dependence is minimized. If you go to much lower values, of course, the energy dependence will be much bigger, and therefore more complicated to separate. Now, what can you do for all this? There is a important new step which is coming up in Europe, and this is the European spallation source, which is in construction in Lund, which could provide 5 megawatts of proton accelerated with the kinetic energy 2.5 GeV, with 14 hertz and a huge intensity of 9 10 to the 14 particle per pulse. This can provide the adequate intensity and repetition rate for the presently proposed Muon cooling program. So this is a new fact. You can see here the picture of the accelerator. It's about 600 meters long, and you can see that it can provide us for the first time the amount of protons that you need in order to be able to do the cooling in a proper way. So this is several other accelerator programs, high energy, have been described in the past in the US, but they all were requiring intensity improvement. So there was nothing like an existing accelerator which we have now there. Now, also LHC is also CERN had considered a possibility to make an upgrade program with a beam of 5 GeV and 50 hertz, 4 megawatts, etc., with 1/9 of the energy being produced by the other system. However, in 2010, CERN has decided on a different alternative, and the project has been cancelled. Therefore, European spallation source is a realistic alternative, and it's the only alternative that we have now at hand if you wish to do in a reasonable short time something which has to do with muon cooling as an alternative. Now, a practical collider as a new facility requires, as I said, first of all, the source of H minuses, a few GeV, stripped in accumulation compression rings of several kiloamps into a beam of about 1 nanosecond in length. Then it requires a pion going to muon and muon channel with a reasonable acceptance and the momentum optimal, which is as indicated about 250 MeV. Then after that, ionization has to come in. You need a robust ionization cooling system, which has to compress the mu plus mu minus bunches in 6D by a factor about 10 to the 5 to 10 to the 6, with a survival rate of 40%. In other words, 40% of you might survive. And then after that, you have to recirculate with the in common muons of both sides at 1/2 of the collider energy, which is 62 GeV. And then you can construct two possible rings. You can construct a ring of 10 to the 32 luminosity, which is only 50 meters radius. Now, remember that. We have talked about electron-positron colliders, which have I have been using now 30 minutes, correct. So I'm still about time. And the system, and 50 meters radius, or if you like to go to much higher 1 TeV energies, you have to go to 10 to the 34 and 400 eV. In addition, the X factor, neutrino factor, is an important new alternative for a European spallation source, where high energy cooled muons produce intense beam on neutrinos and antineutrinos. Now, the Higgs process produced by this system is remarkably clean. You can see here what happens if you take a muon beam into the two main channels, which is H going to BB bar and WW star. You can see here how big how clean the signals are, how little the background is, and you can see how quickly you can arrive to a final result. Now, the cooling process is as described here in detail. I have no time to describe it more accurately. You can see here essentially a number of steps which are used to go from the initial luminosity, which we have of 20 pi millimeter meriradian and 30 pi longitudinally, to something indicated down there, which is 0.04 millimeter meriradian, here 1 millimeter meriradian for that. You can see this is essentially something which is the line through which we want to proceed to do this job. There are one part is particularly important, is so-called peak resonance parametric cooling stage, which is this one here, in which you does something new. You know, in a ring, you have normally collisions which are characterized by ellipses, but if you are on a resonance, you go from ellipse to hyperbola, and therefore you can, in this way, operate in a reasonable situation, in which essentially you can see from this curve what happens here. Without damping, of course, the beam will be unstable, but with the presence of damping, without absorbers, then you have the absorbers which compensate the explosion of the beam, and therefore you get a common result in here, which is characterized by essentially an additional cooling by something like a factor 10 in luminosity, as indicated there. Now, then you accelerate to 62 GeV with a linear collider, which is essentially length of 200 meters. Here you do that, mu plus, mu minus, get accelerated in a recirculating bidirectional linac, 200 meter long, and then they go then to the muon collider, which is about 50 millimeter radius. Now, the crossing point of the beam, it's perfectly straightforward, similar to other system. It gives you beta plus, a beta of about 5 centimeters in the crossing point. Then there are, of course, muon-related background, which are very important, which are represented by the fact that the muon decay to the electrons, and therefore give you background. But the fortunate situation is that the background is in fact dominated to a very narrow angle. This is the kind of addition they have to do for the detector not to remove. And let me just spend a few minutes on the estimated performance. You can see here the proton energy is there 2.5 GeV and corresponding to European spallation source. The proton power 5 megawatts, as I said. The event rates is indicated there. The result is that you collect the luminosity of 4.2 10 to the 32 centimeters squared, and you can collect something like 37,000 events in this situation. If 1/3 of the time you will use the European spallation source to make this program. So obviously the European spallation source will be used by our system, so we put 1/3 of the time available for that, and we get about some 40,000 events per year per interaction region. So 2 interaction regions give you 80,000 events, and you do it for 10 years, and you get 1 million of Higgs particle in all possible channels. Okay, now, there are 2 little questions which I'd like to mention before I close this talk. The muon energy, the point is that the narrow leaks as an unprecedented precision, which has to be of the order of 10 to the minus 5. Now, Tollestrup Araya has developed this idea, and you can see what happens there. The muons are polarized, and when they move along the turn number, they will in fact oscillate because of the polarization, and then you can collect the muon with a muon spectrometer, which is indicated there, and with that system you can calibrate your system. The electron rate is extremely high. There are 10 to the 5 events per pulse. The synchrotron can be measured very precisely. Delta T, they measure to a few hundred kilovolts for every pulse. And the other important question is to find the location of the Higgs. The Higgs now is known to 600 MeV. It will be known maybe to 100 MeV when LHC gets there. But you really want to have a muon collider, we need to find to about few MeV. And therefore, you have to do a measurement, and you see how you can do it. You just make a scan of a reasonable line, and then if somewhere where this is the width of the Higgs as it is known today, and if I see that if you make a proper job, you can estimate the line correctly. Now, what are the advantages of this program? Large cross sections, resonance with a small size footprint. It may fit within the CERN side. Actually, the ESS is the most probable solution now. No synchrotron radiation and Bremsstrahlung program. Precise measurement of line shape and total decay width. Squeezed measurements of all channels test standard model. The cost of the facility provided cooling wheel successful is less than 1/10 of the one of the LHC, so it's relatively modest. What are the disadvantages? Challenges? Low cost demonstration of muon cooling must be done first. A muon in 2D and 3D cooling has to be demonstrated experimentally. Need essentially a ultimate very small center of mass energy spread, 0.03%, which is a big challenge as well. There are backgrounds for constant muon decays, and there is a significant R&D required towards the end of the design. Now, I have another 5 minutes. Should I use another 5 minutes or stop here? That's the question, Mr. Chairman.
Yeah.
What?
Yeah. Can I ask a question?
So you want a question? I can stop here if you want to. I can show a few more things.
I think we can continue.
What?
Continue.
Okay, let's finish very quickly. All right, now, there is a very quickly, there is a initial cooling experiment, which is the idea, which is behind all this. And this is a very small ring, 20 to 40 meters circumference, which we are thinking now of building. And the injection can be produced from an ordinary beam. And all the rest, namely the pions and reduction, the cooling system, muon acceleration, accumulation, storage, it can be constructed later only after the success of the initial cooling experiment has been made. Now, the initial cooling experiment is shown here. You can see it's a very tiny ring. It has 33 meters diameter. It's made out of a large number of solenoids, which are producing the magnetic field. It's injected and extracted before and after the cooling process, and it's made out of many resonators at about 200 megahertz frequency with 12 MeV per meter, and then he has in between some very thin absorbers made out of lithium hydride in order to absorb the signal itself. Now, there are others, a realistic system also being discussed by other people. And now the important thing is that there is a computer prediction. The computer prediction comes from Gian calculation and IQ calculation. And you see that, in fact, the situation is shown there, and they're both in very good agreement. And you can also see that theoretically you find that you get all the cooling you need in order to do what you want. So from the theoretical point of view, you could just take this thing and say, if that thing works that way, you have an answer and you know how to do things, because that's what you need in order to communicate this. Now, the conventional Muon has no advantage. All the problems are in resonance cooling, and peak cooling, which is a little bit more complicated, but this is obviously a major program we have in front of us. So let me conclude. Astroparticle physics accelerator have reached in LHC a construction of 1/4 of a century, an investment of $10 billion. A U plus E minus linear collider with 50 kilometers in length, ILC, and square root of S1 TV is likely novel options, but very long time scale, a huge cost. Short time approval and construction are rather unlikely. In our view, cooling of muons, if viewed a mu plus E minus ring, represents a very attractive alternative, which should be carefully tested with the help of tiny and cheap initial cooling experiment. If successful, it should permit to proceed with muon cooling at a level suitable for high energy mu plus E minus collider, both for the single Higgs production in the S state, a square root of S 126 GeV, with a single conventional ring of 50-meter radius instead of 50 kilometers, is 1.2% of LHC. And eventually, the second step, go all the way to 1 TeV with a ring of 400 MeV radius and luminosity comparable to 250 kilometers CPSV. Provided muon cooling is demonstrated, therefore, both options can be constructed within the existing sites for a cost and time scale which are realistic and financially feasible. Okay, thank you very much.
Thank you. Any question?
Is this working? Back in mid-1990s, Bob Palmer came up with this idea of ion cooling and ionization cooling, and we got all excited about it. And we started the worldwide collaboration towards this. And the Rutherford Lab took the initiative. And of course, Brookhaven, under the leadership of Bob Palmer, started this. And after 20 years, we still don't know. The progress is painstakingly slow. No, it's okay. I'm not against any muon collider. I'm very much towards that, especially in connection with the neutrino factory. I was pushing it. But the problem is whether we will go ahead with the muon collider giving up the ILC. I don't think it can be an alternative. It took us more than 20 years of difficult technology R&D for linear collider. Now, for muon collider, how much do we expect? Maybe 20 years from now, do we know any answer to the ion cooling? No. So I agree with your proposal. This existed for a long, long time. But I don't agree with you to replace this muon collider, replace ILC with muon collider. Well, that's my comment. Thank you.
You can say what you say, but as far as I'm concerned, let me tell you the following. First of all, the muon cooling follows very closely something which I think has ability called antiproton. Antiproton cooling was done at CERN by myself, here, and the others, about 30 years ago. And it turned out to be, it was done by, again, it's 2 phases. The first phase was the initial cooling experiment, in which you took antiprotons and we showed the antiproton could properly cool. And the second phase was the one of taking an accelerator and colliding to be able to do antiproton-proton collisions. Now, I believe that now the situation of the muon cooling, as far as I'm concerned, is rather similar. We have to do a cooling experiment with a very small ring, which we can build in a few years with a very small team of people, and demonstrate experimentally, not theoretically, experimentally, that in fact muons can behave as they should. If that thing works, then we have a chance to build an accelerator, which can go into an existing facility, and which can in fact provide us collisions in the single S state, repeating with the Higgs what has been already done with the Z0. In the case of the Z0, we made the first discovery with the hadrons to get the answer, and we have the equivalent of that with LHC, which is doing the same thing, hadron collisions. Lots of backgrounds, a lot of signal, the signal is there. The second problem is to go into a single S state situation. Was true for the Z0, which has done marvelous physics over 30 years, and many people know that. And the second, and this is clearly what we are now proposing to do with the muons. Now, there is one important new factor which is coming in. You mentioned Palmer and the others. I mentioned that Srinsky and Butker and lots of people discussed those things over many years. It was a quarter of a century ago. At my age, a quarter of a century is a long time. I suppose that for younger people it's not so, but for us it's a long time. And essentially, the question is, At that time, it was evident that many of these points of view were discussed, but there was no real accelerator capable of doing it. Now we have one important thing, that the European spallation source, which produces 9 10 to the 14 protons per pulse, 15 times a second, is now a real machine which is under construction. In 2 or 3 years, it will run, and that gives you plenty of pions and plenty of muons in which you could use this beam for a reasonable way if you want to do it. Now, obviously, you can say the system is not valid. You're shaking your hands. That head is perfectly legitimate. But I have the right to believe that this is a very new option which is coming up. And therefore, this is why I am joining in this argument and try to say we should do something about it, which does not exclude other people to do it. But let me remind you that Fermilab has decided not to do cooling. They've decided to do neutrinos at every possible situation. So neutrinos are being done by Fermilab. So Fermilab is out when it comes to, after 25 years of development, it's out when it comes to muon cooling. And it's quite clear that CERN is also busy making the LHC. And therefore, but we have another interesting alternative, which is a situation that now there is the European spallation source in Sweden, which has all the characteristics which are needed in terms of number and characteristics, etc., to bring in protons in a realistic way. That seems to me that, whether you like it or not, the possibility of using the proton from European spallation source is a real new possibility, which was not there when for instance, Brookhaven proposed, let's do muon cooling, but it was a different machine. Fermilab said, let's do muon cooling, but it was a different machine, which had to be built, constructed. Here we have a machine which works, gives 9 10 to the 14 protons per pulse, 15 times a second. Can you believe it? How many pions can you do with that? How many muons? That's the question. So I like to join in this effort.
As you know, the CERN SPC has reviewed again the muon machine, and I would like you to comment on their conclusions.
Sure.
So one conclusion was positive. They say particularly interesting window of opportunity in the multi-TV beyond click sensitivity range, which I don't know if you think is feasible or not, or is just a way to say no. And then they said, as a Higgs factory, there are superior measurements indeed for the mass and coupling of the muons, but there are other measurements which are less good than E plus, E minus colliders would produce due to the statistics. So I'd ask you if you could please comment.
What do you mean, U plus, U minus? Which?
I said that E plus, E minus, there are other measurements the Scientific Policy Committee claimed, which would be better done for the Higgs couplings in E plus, E minus machines.
I don't know what you're talking about. It's quite clear that if you go to this, if you want to make a bigger ring, I disagree with them. And I may respectfully disagree. If you want to make a linear collider, I think I would say that this is probably a possibility to make 1 or 2 TV, maybe one day, somewhere, somehow. And therefore, the question is whether it's better to make it with muons or with electrons. Now, the linear collider from Geneva to Lausanne, just because we're talking about CERN and CERN, is not a joke. I mean, it's not something you do overnight. I'm sure none of us will see it going in this particular way. I'm not no objection to this, but it seems to me that, in my view, to make in an existing site a mu plus mu minus collider is certainly an interesting alternative, which is worth studying. Now, how do you study it? All this muon cooling needs an experiment. We did the same experiment also for proton-antiprotons. Proton-antiprotons were also discussed equally well all over the world until such a time that a group of people at CERN, something like 10 people, 15 people, got together, used the old-fashioned, already used G-2 ring that Picasso had constructed. And with that, we put a ring. Krinen was there, Petrucci was there, lots of people which we know were there, and they worked together and then demonstrated it works. And when they found it works, that was sufficient to start a new story, because nobody will listen to you unless you do a test. So the scientific committee should wait for us to make a test. When the test has been done, we will decide if it works or not. I believe myself that all the theoretical calculation I can imagine, and many people did, including Palmer, as you mentioned a minute ago, are indicating that there are no big disagreements between the theoretical calculation and what you expect, at least from the point of view of the model. So we are not inventing something unbelievably new. We are not preparing things like the presentation that our friend here, Toft, has shown to us. This is a very simple, trivial question to demonstrate experimentally whether the thing works. This we can do with very little money, with very little effort, and now we have a new fact that we have an accelerator which can produce what we want to do if it's there. Now, up to you to decide whether this is worth enough effort to be able to put it together. It seems to me that this experiment, this device, a 40-meter radius, could be also done in Uppsala. It doesn't have to be done at CERN. And it seems to me that CERN has a big responsibility because you cannot push the LHC all the way to the end and at the same time develop an alternative program. This is the decision that the SPC will have to take. But as far as I'm concerned, I see that, to my view, the initial cooling experiment is trivial activity, which I certainly will do myself very, very decent. With all due respect for those people which a quarter of a century ago worked on these things. And in those conditions, if the bloody thing works, I think I will have a case. If the thing doesn't work, we will know it does not work. And this is the kind of next step which you have to do. We have to do one step at a time. But if we have that to make a ring of 40 meters radius, is not something that requires the kind of descriptions that you're talking about of making the ring of 4 times CERN surrounding the whole of the Geneva Lake area. Although I agree with you that there are lots of people, including the directors for research of CERN, which in fact think that that is the way to go. But I mean, the question is, I think it is a question which has to be debated, to be discussed. In my view, it seems to me that I have in my old age enough strength and interest to spend a little bit of time to contribute and to add what other people have already done and try to make this initial cooling experiment, which is something I can know how to do. And if it works, we'll change the world.
Everybody assemble at the atrium for the photovoltaic taking. So please assemble that first before.
Thank you.
Very good. Thank you.